Hi, I'm Nick Moffat with Verisurf Software. Today I'll show you how to use the Master3DGage to align, inspect, build, analyze, and reverse engineer parts and assemblies. The Master3DGage is a complete portable solution that enables rapid in-process and final inspection of precision machined parts. And it's faster than any other method. I'll give you an example. Let's say I have a part on a machine tool and I want to check contour before the next operation. I'll start by moving the arm into place. Then I'll load a CAD model of the part and run an alignment. The system uses bullseyes to guide me to the alignment points. And when the alignment's complete, I can go directly to inspection. As I move the probe across the surface, I get an analysis of the deviation between the part and the model. And when the measurements are complete, I have an analysis of the part. I'll add balloons to it to show the limits, save it, and I'll create a report. When I open up the PDF file, I can see the part's intolerance and I'm ready to continue my run. The Master3DGage is the fastest way to align, inspect, report, which makes it ideal for rapid first article inspections. It supports continuous process improvement. It eliminates programming, which makes it faster than a fixed CMM for most applications. It provides a common platform for manufacturing and inspection, and it adds tool building and reverse engineering to your inspection tools. Finally, it improves inspection throughput and generally lowers the overall cost of quality. We've seen an overview of what the Master3DGage does and how it can benefit your manufacturing process. Next, we'll take a closer look at the system. The Master3DGage system comprises both hardware and software. The gauge itself is a 6-axis articulating arm CMM that uses a hard probe to measure 3D points and point clouds. The arm has a 4-foot volume, or a 2-foot reach in any direction. It uses a Tessa mount that allows us to swap probes without having to requalify. Accuracy is between 2 and 7/10,000ths of an inch for characteristics such as position or length, depending on the size of the object we're measuring. And for characteristics such as form, the accuracy is 3/10,000ths. Despite the high precision, the Master3DGage was designed for shop floor use. It communicates via USB or Wi-Fi, and it runs on either battery or AC power. The combination of durability, size, and wire-free operation make it ideal for on-machine inspection. The Master3DGage is accurate, portable, durable, and easy to use, but what really makes it powerful is the software. We'll look at that next. Verisurf recently introduced a new and improved version of the Master3DGage, and I want to review the enhancements before we continue the demo. The new model offers the same portability, accuracy, and competitive pricing as the original, and it retains the same basic design. Measuring volume is 4 feet, or 1.2 meters. Both USB and Wi-Fi communication are available, and the system runs off of either AC or battery power. The new Master3DGage is certified to the ASME B89-422 standard. Volumetric accuracy is 25 microns, or 1,000th of an inch, and point repeatability is 14 microns, or just over 0.5 The new Master3DGage also offers a number of design improvements. Absolute encoders enable instant startup, so you don't have to initialize the arm. The Tessa mount, which allows quick probe changes, now features a keyless locking system. A new ergonomic wrist and single-piece counterweight make operation even easier. The system includes a magnetic base kit for faster and more flexible mounting. The optional certified length bar allows user verification of system accuracy, and we highly recommend it. The new Master3DGage is still portable, accurate, durable, and easy to use. In the segments that follow, I'll show you how to use VeriSurf to align, inspect, build, analyze, and reverse engineer using the old model, but the workflows are identical using the new hardware. The Master3DGage runs inside VeriSurf's metrology software, which is built on a CAD platform, giving us full CAD design capabilities. CAD is important for reverse engineering, but it's also very helpful when inspecting complex parts. For example, we can analyze the elements in the model. We can pull dimensions from the model. We can even manipulate the model, for example, to change or flip surface normals if necessary. Tools such as colors, levels, and attributes allow us to easily manage large part assemblies. VeriSurf integrates design, inspection, tool building, analysis, and reverse engineering all into a single application. Finally, VeriSurf is designed for both print and model-based workflows. I'll start by loading a model of our demo part. VeriSurf reads all popular CAD files, CATIA, NX, ProE, SolidWorks, in their native format. This helps avoid the limitations of neutral formats such as STEP and IGES, which VeriSurf can also read. I'll start by opening a Parasolid version of our model. When VeriSurf loads a native model, it stores it in the MCX format and leaves the original file intact. All of the data that we accumulate, measurements, reports, analyses, etc., are stored with the model. Using one file simplifies handling and prevents data loss. I'll reopen our model file using the MCX format. We have the model loaded and the part is set in place. In the next step, we'll align the Master3DGage to our part. After we load a model, we typically align the device to the part so that we can get real-time feedback on tolerance condition. VeriSurf offers a variety of ways to align the device to the part. We'll use auto-align since it's the easiest way to align to a model. We start by creating alignment targets on the part. If our model has datum targets, that's where we place the alignment targets. Otherwise, we position them so they control the position and orientation of the part. I'll choose Create Target and then place 4 targets on the top, 2 on the front, and 1 on the end. To begin the alignment, I choose Run Auto Align and then follow the bullseye around the part. After the 3rd target, VeriSurf guides us to the remaining points. And when the alignment's done, VeriSurf best fits the device to the part and shows us the results dialog. We can use the dialog to review and modify the results if necessary. We can create a report. We can reject and rerun the analysis. And if we choose Auto Accept, VeriSurf shows us the dialog only if the deviations here exceed the threshold set here. This is what we normally do. Since the check marks are all green, indicating that the alignment's good, we'll choose Accept. And when I do, VeriSurf puts us into Inspect Build mode so that we can verify the alignment. As I move around the part, VeriSurf shows the deviation between the part and the model. This final check validates our entire alignment workflow. In order to see this good of a match, we had to have the right part, we had to have the right model, the device has to be working right, couldn't make any mistakes. So it's a validation of the whole alignment workflow. Auto Align is a very powerful alignment tool, but it's simple enough for beginners to learn, and it has the built-in check of Inspect Build mode to verify the alignment. The gauge is now aligned to the part, In the next step, we'll see how Inspect Build mode calculates the real-time deviation. We used Inspect Build mode to verify the alignment of our device. Inspect Build is a special measuring mode that shows in real time the deviation between a part and the corresponding features in a CAD model. When we're inspecting a part, the deviation reflects the material condition. When we're moving a part into position, the deviation shows how far to move and the arrow points the direction. Since it serves both purposes, we refer to it either as Inspect or Build depending on our goal. As we move around the part, VeriSurf highlights the nearest nominal surface and drops a perpendicular from the probe center to find the nominal point. VeriSurf then applies probe compensation along that line to find the actual point. The distance between the actual and nominal represents the deviation. When the probe is above the surface, the deviation is positive and the arrow points towards the surface. When the probe is below the surface, the deviation is negative and the arrow points away. As I move around the part, notice how the deviation arrow, the deviation text color, and the slider color all change to reflect the tolerance condition. If I display MBD, notice how the tolerance changes to reflect the highlighted surface. We can also use digital readouts for a more detailed representation of the deviations in build mode. We've seen how Inspect Build mode works. Next, we'll use it to inspect and then to position our demo part. The Master3DGage is aligned to the part, so when we inspect the part, we'll assume the deviations are due to machining errors. I'll run Inspect mode and then check a few points on the top surface. I'll use single point mode. Notice that the deviations are represented as arrows with the deviation text. If I shim the surface and place the probe on top, notice that the build arrow points down. When I record the deviation arrow points up. That's because the build arrow shows where the surface is supposed to be, and the deviation arrow shows where it actually is. I'll undo that point and remeasure it without the shim. When I press Escape, VeriSurf creates an analysis object in the data tree. If I highlight it, I can see the distribution of errors in the color bar. If I double-click the analysis object, we can change the way the deviations are rendered. For example, we can hide the deviation text entirely. We can add borders to the deviations. We can change the arrows to cones or to lines. I prefer arrows, so I'll leave it alone. We can render it as 3D spheres. We can use the probe radius. We can use some fixed radius. Or we can use a multiplier to make the size of the sphere proportional to the deviation. Go back to the arrow display. If we enable Use MBD Tolerance, which is the default here, then each point is analyzed according to the surface profile callout in the MBD. If we disable MBD Tolerance, then everything is analyzed according to the global profile tolerance. We'll reselect it. Once I have the deviations rendered the way I like, I can choose Set as Default, and then subsequent analysis objects will be rendered the same way. I'll go ahead and do that and then choose OK. I'll now add balloons to the deviation object. I can auto-add balloons and do something easy. I'll just show where the limits are, the two highest and the two lowest points. They're flagged with balloon callouts. I'll save that. Now I want to create a report. So I'll highlight the object to get the color bar showing. Click the report button. and I prefer to see the screenshot above the deviation text, so I'll change the order. VeriSurf gives us a lot of options for how we want to create the report file. When we create a report object, we have a container that stores the analysis data. We can output that in different formats such as PDF, Excel, HTML, Word, etc. I prefer PDF. One of the reasons being, if we look in settings, we can secure PDF files with a password. If we go to General Options, we can use the Change Logo button and select the Master3DGage icon. So now when we create a report file, we have the Master3DGage in the header. So we have a simple report for a simple inspection, 6 points. We'll close this and then we'll scan the part using continuous scanning. So I'll hide this deviation object, reselect. When I choose P, I can toggle into continuous mode. So as we saw at the beginning, we just scan along the surface, get real-time deviation analysis. Capture points on the top. And then I'll escape. So now we have a second analysis object. I'll unhighlight that. That was our first. That's our second. We'll add balloons to the analysis. Only this time we'll add 8. Choose Apply, save the result. And again, we'll create a report. Highlight the object, choose Report, change the order. And again, we'll create a PDF file. So the process is very similar. This time we get a little more data. Now, you notice that when we were in Inspect Build mode, hide that. And we'll switch back to single point mode. As soon as I record a deviation, the real-time text updates and I no longer see the recorded deviation. If we want to get around that, we can choose Device Display Settings, Show Static Deviations, and now when we go back into Inspect Build mode and I record a deviation, I don't see anything until I record the point, and then the deviation stays on the screen statically until I update it with another recording. So that's helpful if you're working far away from the computer and you can't see the small deviations on the model itself. We've seen how to use Inspect mode to check parts in real time. Next, we'll see how to automate the process. Using Inspect mode to check a part is very efficient, but we can make it even easier by automating the process. Automation improves process control by ensuring that all parts are checked the same way each time. If we open Auto Inspect, we can see the 2 reports that we created earlier. If I double-click on Automation, it opens the Report Manager, and if I run the report, we can see it's identical to the first one we created. In VeriSurf, creating an automation is the same as creating a report. To run the inspection, we choose Clear All and then select the green Run button. VeriSurf targets the inspection points just like in Auto Align. I have this set to automatically record as we pass by the point, so I don't even have to trigger it. When the last target's measured, the inspection is complete, and we can create a report just like we did before. Now this process works well if we can fixture each part in the same orientation. As an alternative, we can even automate Auto Inspect so that the alignment is part of the automation. For example, I'll open the report for this automation, highlight the targets, choose Command, and then I'll move Auto Align up to the top of the list. Now when I run Clear All, and run the automation. We're first guided to measure the alignment points in auto-align. And when the alignment's done, we're prompted to measure the targets. We've used real-time deviation analysis to inspect surface profile. Next, we'll use it to position our demo part. When we position a part using build mode, we assume the part is good and the deviations are due to errors in the position of the part. We refer to this use of real-time deviation analysis as build mode because it's often used to build tooling and assemblies. However, build mode is not restricted to building tooling. We use it anytime we want to position an object in 3D space. Normally, we'd align the device to the basis of the model by measuring features with known CAD values. We'd then use build mode to position physical objects by moving them to their nominal locations. Since we're already aligned to the basis of the CAD model, I'll simply move it and we'll build it back into position. I'll start by running inspect build mode to verify the alignment of the device to the part. Looks correct. Now I'll move the part off slightly and we'll move it back into position. I'll start by selecting the circles and building to center lines. This is a quick way of getting the part roughed in. Put the probe in the hole and move it in the direction of the arrow. Get it close. The trick here is to move one without the other. Once we get it close, cancel out, escape out of the circle selection, and then we'll build the surfaces. Before we do, I'll turn on the GD&T. And get it a little closer. We can use the surface profile to control our build tolerance. In other words, as long as the surface profile shows up correct, we'll consider that the part is in the right location. There's always a tendency to want to build to 0, but what we want to do for economic reasons is build to green. We want to position the part so that it's in tolerance, not necessarily so that it's perfectly 0 everywhere. I'd say that's close enough for what we want to do. This is obviously a very simple example of a build application, but the same technique is used for more complex structures. The part is now in position. We left it out slightly. In fact, we'll tweak it a bit more so that we have something to do for our next step. We've already seen how to use inspect mode to check our part in real time. In this step, we're going to repeat the same analysis using measured point clouds. I'll start by measuring point clouds around the sides and the top. Notice that this time we don't get deviations in real time. The point clouds are just raw probe center data. So now we have essentially the same measurements we took before. We need to analyze them. On the Analysis tab, I'll highlight the point clouds and choose the Analyze button. We get another analysis object. It's similar to what we saw before, but the deviations are much larger because we left the part intentionally unaligned in the last step. We know the part's good and the large deviations are just due to a misalignment. I'll hide that analysis object, select the point clouds, and run a best fit. Before we do, I'll analyze the data to get a starting point and then run the fit. When the fit's complete, we see the improvement, and we can toggle between them to see the before and after. Also notice that if I go to the Measure tab and run Build mode, we should see large deviations because we left the part out of alignment. But because the best fit is also applied to the device, it's aligned as well. We've already seen how to add balloons and create a report. We won't do that on this analysis object. Instead, we'll see how to analyze existing data. I'll save our current file, and then I'll browse to the model. Now I want to load the point cloud that we want to fit and analyze. I'll bring in the data, and I know that it's probe radius 750. It's laser tracker data, so I want to make sure to enable that and enter the correct value. When I choose OK, I now have a point cloud and a model. The first step is to create auto-align targets on the points. And then I can run an offline auto-align to fit the data to the model. And when I choose Accept, now they're aligned. It's slightly off from the 750 probe radius, which is correct. Now all I have to do is go to the Analysis tab, choose the point cloud, and run Analyze. So we can take data that we measured directly within Verisurf. We can also analyze data that's given to us from other sources. Inspect mode, which we saw previously, and Analysis, which we saw here, are very powerful tools for model-based inspection. Next, we'll measure and analyze prismatic features. The workflows we've seen so far have all been model-based. We aligned to a model, we inspected the surfaces in the model, and we used model-based probe compensation. Next, we'll look at print-based analysis and reporting of prismatic features. We'll align the Master3DGage to the frame of reference shown on the CAD model here, but since we're not going to use the model, I'll open a blank file. I'll start by measuring a plane on the top of the part. We'll use that to define X, Y. Then I'll measure two lines, one to define X and the other to define the Y axis. Press Escape, look at our data. Now I'll run Feature Align. That looks correct. If I choose F9, I can see the alignment is at the world frame. And if I go into point mode, place the probe at the origin, I can see the Master3DGage is also aligned. We'll start by measuring a few features. I'll begin with the cylinder on the ID circle. Then I'll measure a cone. Then I'll measure a slot. I'm displaying the feature measurements as probe hits so that we can see how probe compensation is accomplished. Go into top view, look at the data. We can see that the slot is tangent to the outside of the probe hits, which makes sense because we measured the slot on the inside. Same with the cylinder and same with the cone. For 2D features such as slots, Verisurf uses a combination of projection planes and the feature itself for probe compensation. And for 3D features like cylinders and cones, Verisurf uses the geometry of the feature itself. We'll continue on with sphere measurement. At this time, we'll switch into continuous mode. Press done. I see the sphere, I see its form. Continue on with the hole pattern. If I make a mistake, I can hit U to undo the last probe hit and continue the feature. And if I don't catch the mistake before the last measurement is made, I can press undo to delete the whole feature and remeasure it. I'm going to switch to point mode to measure the two end planes. We'll start with the left end and measure it as 4 points. For the right end, we'll measure it as a point cloud. We'll take the 4 points and we'll fit them to a plane. We'll do the same thing with the point cloud. Right-click, fit plane. Just like the other features, the probe compensation is done in the correct direction. If I use the statistics button to analyze the data, Verisurf tells me that there are no CAD entities, and that makes sense because everything we see on the screen right now is measured. I'll select all the features, choose Export to CAD, blank the database. Now if we go back, we can see that CAD features have been created for all of the measured features. We also have the option of creating CAD features on the fly, but that's more of an application for reverse engineering. I'll undo the CAD features, redisplay the database. The statistics box at the bottom of the data tree allows us to get real quick report on relationships or characteristics of single features. For example, if I pick one feature, I get characteristics such as its form, size, position, which alignments it's using, etc. If I pick two features, I get the relationship between them, such as the angle and distance between circles or the angle between lines. It's a quick way of doing a check without reporting, which we'll see next. We've seen how the Master3DGage measures prismatic geometry. Next, we'll see how to analyze and report the results. We briefly saw the report manager when we reported our analysis and inspection results. Now we'll take a closer look as we analyze and report our measured features. For this report, I'll use the circles of the hole pattern in the two end planes. Select the features, choose the Reports button, and the data appears in the Report Manager. If I select a single feature, I can see its characteristics in the Details pane. We use these fields to change the nominal and tolerance values. I'll change the nominal for Circle 1 so that we can report its position. The toolbars in the Report Manager allow us to create CAD values, to construct measured features, and to add GD&T callouts to the report. I'll use the Construct toolbar to create first the plane and then the circle through the hole pattern. I'll select the circles, choose Construct Plane, and then with the same selection I can use Construct Circle. Next I'll construct a line from the center to Circle 1 and Circle 2. Select the center, Circle 1, choose Construct Line, and then do the same thing for Circle 2. I now have the two lines. I can select them and calculate the angle between them. I know the nominal should be 45, so I'll enter that. And now I'll construct the distance from the overall circle to circle 1. Construct distance and enter its nominal value. Next, I want to report the parallelism of the two end planes. I'll select the two planes and then choose parallelism from the GD&T toolbar. Finally, I'll report the position of circle 1. I only want the final values, so I'll highlight them before I create the PDF file. So there's our report on the prismatics using the Master3DGage logo. I referred to the measurement, analysis, and reporting of prismatic features as a print-based workflow, but it works equally well, if not better, with a model. I'll use the merge function to merge in our original CAD file. Since we use the same part frame for our alignment, the data is already aligned to the model. I'll remeasure one of the circles. And then add it to our report. If I highlight the circle, I can see that the CAD values are already defined. In this case, since we were aligned to the model before we measured the feature, Verisurf automatically associated the nominal circle with the measured circle and entered it into the report manager. If we want to add nominal values to existing features, we can, for example, right-click a circle, choose Set Value from CAD, and then choose the circle out of the CAD model. Now the nominal value is defined. Our report displayed results in the single part frame to which we were aligned. Next, we'll see how to report in multiple frames using the WCS function. A WCS is a frame of reference we create on a model to define a new view of the CAD features. In a print-based workflow where we don't have a model, we use WCS from measured features to construct a frame using measured data so that we can report in multiple datum alignments. Let's say our print requires that we report the whole pattern based on the top plane, the constructed circle, and circle 3. I'll take the constructed circle and export it to measured so it appears in the data tree. I'll run WCS from measured features. We use plane 1 to define the primary plane. The line from the constructed circle to circle 3 defines the axis, and the origin is set at the constructed circle center. When I choose OK, we see the WCS defined at the center of the whole pattern. Now, if we open the report, we can change the WCS for any of our features to report in the new alignment. I can change multiple features at once by selecting them and then choose Update WCS from the speed menu. When we generate the report, Verisurf displays the WCS that's assigned to each of the features. We've covered just a fraction of Verisurf's capabilities for measurement and reporting. The reports we created here can be automated as we saw earlier. With multiple feature types, formats, and settings, we can measure, analyze, and report just about anything. For the next step, we're going to reverse engineer a part. Verisurf's reverse engineering tools enable mixed modeling using prismatic features, meshes, surfaces, and solids. Moreover, we can take advantage of the many CAD design tools inside Verisurf. For this example, I'll scan and then surface the top of the demo part. I'll start by measuring a reference for our part. I'll measure the plane on the table. And then I'll measure 2 lines for the axes. This isn't strictly necessary, but it's always nice to have a basis of reference for our data. Escape, choose feature align. Everything looks right. Turn off our features. Okay. Now we'll scan the top using continuous mode, 1/4 inch spacing, gather a couple of hundred points. On the reverse tab, I'll highlight the cloud and choose patch. The fit parameters allow us to control the accuracy and the complexity of the surface. I'll verify the probe offset and then choose create surface. When the surface is created, we can look at the standard deviation and the UV control, and they're within the parameters that we set, so the surface looks good. I'll accept the results. So we have a surface that the parameters indicate is good, but how can we check it? If we go to measure, we can run build mode and check dynamically how well our calculated surface matches the part. That check looks great. Another way to do it, escape out of build, we can go to the analysis tab, select the cloud, and analyze it. Again, it looks good. The color bar indicates all the points are in tolerance. If we wanted to, we could then create a report that showed the accuracy of the surface. The data from the Master3DGage is traceable, so we have a way of creating a report and proving the accuracy of the surfaces that we create. Being able to measure, reverse engineer, and verify is a great benefit of having an integrated metrology solution. For the second example, I'll surface an existing mesh. I'll open the grip file. We don't need to save what we just did. And now I have a mesh that represents some kind of a grip. I'll select the mesh on the reverse engineering tab and choose auto surface. We'll accept the defaults. We're not interested in anything accurate, just quick. And I'll choose create. Now, when the surface is complete, we can perform an analysis, but we need a point cloud. We'll take the mesh, we'll export the data to a cloud, and then hide the original mesh. Again, I can go to the Analysis tab, select the point cloud, and analyze it. In this case, using a color map is probably a better choice than lines. Say OK. And I see blue and red, so I want to annotate that. I'll go ahead and choose balloons. It's worked in the past. We'll just apply limits, save. So we can see what the min and max deviations are. And of course we can go back and tweak the surfacing parameters if we want, but for our demonstration this is sufficient. These are just two simple examples of Verisurf's reverse engineering tools. Verisurf's integrated solution enables reverse engineering workflows that include data capture, cloud editing, meshing, surfacing, and solid modeling, and conclude with surface validation. That concludes the presentation, and thanks for watching. I hope I've given you a good appreciation for how Verisurf and the Master3DGage can increase your inspection, fabrication, and reverse engineering capabilities, increase your inspection throughput, and reduce your overall cost of QA. For more information about Verisurf and the Master3DGage, or to schedule a demonstration, please call us at 888-713-7201 or email us at sales@verisurf.com.